Next case study for discussion is 0 power n square where n greater than or equal to 1. So which means all strings that are generated, they are of this type. So 0 power 1 square, 0 power 2 square, 0 power 3 square, 0 power 4 square and so on. Okay, so the length is a perfect square. We want to show that things like this is not. Let's choose w to be 0 power n square itself. Clearly we see w is at least n. And now with this we need to come up with a decomposition. So we do not know how many zeros are there in v. So let me call 0 power k. We only know v is at least 1. To its left 0 power r. To its right 0 power n square minus r minus k. Okay, so this part is u, this part is z. Now let's look at a string w prime which is 0 power r, 0 power k to the power I, 0 power n square minus r minus k. So we want to choose one appropriate value for I. With that we will argue that w prime is not part of this. As before, let's simplify 0 power r, 0 power k and 0 power k to the power I minus 1 times 0 power n square minus r minus k, retaining one copy and this side I minus 1 copies. So when we simplify, we get 0 to the power n square, this one together times 0 power k times I minus 1. So this gives you the following. So w prime equals 0 power n square times 0 power k times I minus 1. Okay. Now we need to choose one value for I such that the resulting expression is not a perfect square. And in the earlier one, we wanted to choose one such that it is not a prime number. So we were looking for the value of I such that it was on simplification, it was giving us, it's a composite number. Okay, so on the similar line, let's attempt the following. So now let me choose I to be 2. Now we get 0 power n square and times 0 power 2 minus 1, so it is this. So which means it is 0 power n square plus k. So what is the idea? Idea is the following. We need to show that this n square plus k is not a perfect square. Meaning, claim n square plus k is not m square for any m greater than or equal to 1. But in an attempt to prove this, we know something about k. Let's use that property and show this. We know that k is representing the cardinality of v, which means k must be 1, and uv is at most n. U can be empty, which means k is at most n. So k is between 1 and n, correct? And because k represents cardinality of v and it is at least 1 and at most n. Now let's look at n square plus k. So this n square plus k could be n square plus 1 or n square plus 2, so on up to n square plus n. This is all possible, right? But n square plus 1 is not n square plus 2n plus 1. What is this? This is the next perfect square, which is n plus 1 the whole square. On the similar line, n square plus 2 is not this, n square plus n is not this. So all of them is not n plus 1 the whole square. So what is that we have shown through this argument is the following. You have n square, because it is n square plus k, if at all this number is a perfect square, it is going to be the next one. Okay, it is going to be n plus 1 square or n plus 2 the whole square and so on. But what we have shown is you have n square and n plus 1 square in the spectrum, and n square plus k is between these two. So n square plus k is between these two. So k is at least 1, which means it is neither n square, and through this argument we see that nor n plus 1 the whole square. Therefore n square plus k is strictly between this and this. So what is this argument giving us? Here is the value of I such that this one is not in L. This implies that L is not regular. So what is our approach? Choose a string, and whatever may be the decomposition, identify a string such that it is not part of L. But whenever some computation is involved, checking perfect squareness or primality, the argument is little involved. It is not as straightforward as when we do pattern matching case studies like 0 power n, 1 power n and so on. So now here is w prime. One has to choose I carefully. Let me choose I to be 2. Our objective is to show that the length of the string is not a perfect square. What I am trying to do as part of this is choose I such that this expression is between n square and the next perfect square, which is n plus 1 the whole square. And we know k represents the cardinality of v, so it is at least 1 and at most n, which means the possible values for n square plus k are n square plus 1, n square plus 2, so on up to n square plus n. And this is not same as n square plus 2n plus 1, which is n plus 1 whole square. On the similar line, none of them are n plus 1 the whole square, which means the value n square